Hello and welcome back to this deep dive into 4.10 lesson. Am I dealing with shiny pencil syndrome today? It's a little shiny. Let's see. Oh well. I wonder if I can turn this light on. Nice. Is that better? I'll say it's better. Darken this down. Darken this down a little bit. No, now we're really doing. Now this is a great video all of a sudden. Top 10. Solve for the missing side and angle measures in a right triangle. Right triangle, missing sides. We already can do that, but this is new. We're going to find the missing angle measures, even if we have only the 90. Well, we can find missing side lengths and angles in a right triangle if two sides or two angles are known using the Pythagorean theorem or the angle sum theorem for triangles. So what they're saying is, if it's a right triangle and you know two sides, then you can figure out the third side using Pythagoras. Or if you know two angles, then you can figure out the last one, because 90, 60, remember it has to add up to 180. That's called the angle sum theorem for triangles. So using those is one way to do it, if you have two sides and two angles. But what information do we need to find missing measures in a right triangle now that trigonometric ratios are available as computational tool? Turns out you don't need to know as much. One side, one angle is fine. Or wait, not one side, one angle, but one angle, two sides, or two angles, one side. I don't know. How can we use trigonometry to make indirect measures? Okay, let's move on. Part 1, pick a side. Look at what 6th period gets to play with. Part 1, pick a side. Andrea and Bonita are resting under their favorite tree before taking a nature walk up a hill. Both girls have been studying trigonometry in school, and now it seems like they see right triangles everywhere. For example, Andrea noticed the length of the shadow of the tree they are sitting under and wonders if they can calculate the height of the tree just by measuring the length of its shadow. Diagram. Shadow. Tree of unknown height. It's got a shadow here. They know the shadow is 40 feet long. They've also measured this angle. So this is actually like the quiz. We're just looking for this side, x, but we know this angle, 50, and I guess we should finish the problem. Back to the other one. Bonita thinks they also need to know the measure of an angle, so she checks an app on her phone and finds that the angle of elevation of the sun is the current location and time of day. At the current time of day is 50 degrees. In the meantime, Andrea has paced off the length of the tree's shadow and finds that it is 40 feet long. How might Andrea and Bonita use this information along with their knowledge of trigonometric ratios to calculate the height of the tree? They can find the value of any trigonometric ratio they may need using a calculator. So, tree, shadow, angle to the sun, unknown. Feet. Okay, so tan is our friend. The tangent ratio of 50 degrees is some number we will find, but it specifically, in this case, needs to be x over 40. And we shall multiply by 40 to isolate the x and figure out what it is. And tan 40 equals, 40 times tan of 50. 40 times the tangent of 50 degrees Calculator. "47 feet tall." 47.7. Okay, so that's just a story problem. We did that. We did this technique. We've done this. We did this last week. Uh-oh. The story continues. After their rest, Andrea and Bonita are going for a walk straight up the side of the hill. Andrea decided to stretch before heading up the hill, while Bonita thought this would be a great time to get a head start. Once Bonita was 100 feet away from Andrea, she stopped to take a break and looked at her GPS device that told her that she had walked 100 feet and had already increased her elevation by 40 feet. With a bit of time to waste, Bonita wrote down the trigonometric ratios for A and angle B. Aha! 100 feet total through space. And her elevation had gained. So now... When Andrea caught up, she said, "What about the unknown angle measures?" Oh, and I guess we should just Pythagorize this real quick. $1,600, 10,000, 1,600. B squared equals 80,400. Take the square roots, and I believe that is B equals 60. Is that true? Wait. 80. There we go. Wait, 84? Oh, I better just figure this out then. $91.7. Better double check this though. 10,000 minus 1,600. 84,000. Yeah, that's what I did. Okay, so this is the size 91.7. So replace all these x's with 91.7s, I guess. That's what they wanted us to do. Now we're able to ask, what about the unknown angle measures? When I was at the bottom and looked up to see you, I was thinking about the upward angle. It's called the angle of elevation. Upward angle measure from me to you. Based on your picture, this would be angle A. Yes, indeed. Bonita wrote the trigonometric ratio of sine A equals 2/5. Oh, we have sine of A equals 40/100ths, but simplified, of course, that would be 4/10, which, of course, would be 2/5. And asked, so how do we get angle A? Together, the girls talked. Oops. The girls talked about how this was like thinking backwards. Instead of knowing an angle and using their calculators to find a trigonometric ratio, like they did while working on the height of the tree problem, they now know the trigonometric ratio and need to find which unknown angle value goes with that. In other words, we know the ratios on this right triangle, and there's only one. It's like Highlander. There can be only one angle for angle A, that makes these ratios. So if only we had a big book of ratios, we could look up this ratio, 2/5, and we could figure out what angle goes with this. What angle goes with 2/5? Bonita notices the sine to the -1. This is actually pronounced inverse sine. Inverse sine, or arc sine is another name for this. She notices that funny button, and theta is this is the Greek letter theta, and it stands for degrees, it's an angle measure. But she notices the inverse sine button on her calculator, and she wonders if this might work in an inverse trigonometric ratio way, undoing the ratio to produce the angle. I don't really look at it that way. She decides to try it out and produces the following input on her calculator. Let's reproduce it. Notice this it's for inverse. Now, hey, there we go. Sine to the -1. Inverse sine. Don't ever say sine to the -1. I'm saying that because that's what it looks like. But when you do this, you'll say inverse sine, 23.5. Oh, just like what they have. Look at that, look at that. How might this output convince Bonita that her assumption about the calculator was correct? Well, obviously, take the sine of 23.578 degrees and see if it spits out 0.4, because that's 2/5. 2/5 is 0.4, because 0.4 is 4/10, and that's 2/5. Okay. So let's see. I need to change it back to regular sine. Sine of 23 degrees. Oops. 23.578 degrees. Oh, 0.3999999. That rounds to 0.4. I kind of... Okay, do I have time for this? Sine of 2/5. Let's 5782. Let's round out one more thing. So regular sine of 23.5782. Dang, there we go. Now it's 0.4. Because I went out one more decimal place and rounded up at that decimal. So we got to the 0.4. Yeah, so this shows you the complication. Well, it's not a complication. It's just that the ratios, either the ratios are nice and then the angles are crazy, or the angles are nice and then the ratios are crazy. But only at 45, 90, and I think 30, 60, 90, those are the only ones with nice angles and nice ratios. I'll let you write a college thesis paper about why that's true. Oh. So this should be approximate. How's the other book doing? Approximate doodle. We're almost done. Hold on, hang with me. They're saying we can use the triangle sum now that we have a see what's 90 minus 23.578. 66.4218. There, so now we have all the degrees. But we can also inverse cosine this thing on 4/10. Yeah. Let's see. So we know that cosine of b is 4 over 100. Let's switch to this. I'm just going to keep, I'm not going to use this is 2/5 again, but I'm just going to leave it like this. Okay, check this out. Before we were just abstractly treating cosine b as some number, but now we can start thinking of it as an operation, and we can algebraically crack into it by taking the inverse of both sides. So this is like an algebra operation. Inverse cosine undoes cosine, gets us b. Inverse cosine of this number, let's find it. Inverse cosine of this number. Oops. Where was I? There it is. There it is. Dink. Oops. Whoa, what's going on? All right. Find all the unknown values for the given right triangles. This is not funny. Okay, this is funny. Eight squared, 64. Forgot to write this down, sorry. Okay, it's 8 squared, 64 plus 144, which is 12 squared, equals c squared, 210, 208. All right, now we get to use my favorite, inverse tan. Inverse tan of the ratio 8/12. $33.7. Now if we do it from B's perspective, inverse tan of 12/8. 56.3. Problem solved. Bonita and Andrea started talking about all the ways to find unknown values in right triangles and decided to make a list. Oh, good. What do you think should be on their list? Be specific and precise in your description. For example, trigonomic ratios is not specific enough. You may use the following sentence frame to assist with writing each item in your list. Okay. Well, they did not give us room to write all the stuff we need to write. But 6th period has room. So I don't know. I guess use this space. Use this space to write your sentences. I don't know how to spell sentences. Don't make fun of me. I don't think there's a C here. Meanwhile, when given the op and opposite and adjacent of an unknown angle, you can find the angle by taking the inverse tan. Let's try to shorten this up. If you have the op and hype, you can find the angle with inverse sine. By the way, these are sometimes known as arcsine and arctan. Oh, I'm not on there. So time for a little aside. Let's do this, 27, 9, 3. So this is 3 to the third. This is 3 squared. This is 3 to the first power. So next will be 3 to the 0th power, not 30, but 3 to the 0 power, and 3 to the negative 1 power. So let's figure out. The pattern is divide by 3. Divide by 3. What's 3 divided by 3? 1. What's 1 divided by 3? 1/3. So notice how 3 to the first and 3 to the negative first are inverses, because what's 3 flipped over? 3 flipped over is 1/3. So this little symbol to the negative 1 has become associated with undo it. And then mathematicians love to multiply, so what's 1/3 times? It's 1. So multiplying by 3 is undone with 1/3. Finding the sine ratio of an angle is undone by taking the inverse sine of that ratio. An inverse, hey, that's associated with this negative 1. But then that became this. But this makes no sense, because if you flip this over, you have 1 over sine, let's say, of A. Well, that's not how sine gets undone, because sine's not multiplication. So why did the multiplication reverser become associated with trigonometry? It should never have been. So that's why on many calculators you will now see arcsine. Arc from, I think, Spanish, meaning arc. I don't know what it means. Just kidding, I'll look it up. Okay, I could not find the reference I was thinking of, but down here we go. The notation sine to the negative 1, introduced by John Herschel in 1813, are often used as in English language sources. So in Mexico and Latin American countries, they don't use sine to the negative 1. They use arcsine. That's why I was associating it with Spanish. But I guess it's worldwide. English speakers are the only ones who do these weird things, and someday, hopefully, I mean, it's fine, it's cool, but it doesn't mathematically make sense with that little negative 1. So I hope we switch to just using arcsine. All right. Where are we? I think we're done. There's one more to write, go ahead and write if you have how do you use arc cosine or inverse cosine? Inverse cosine is a fine way to say it too. Are we still going? Angles of elevation and angle of depression.
Clear.
Horizontal line. From the horizontal, if you look up, the angle from the horizon to your line of sight is called the angle of elevation. Likewise, if you are looking down, the angle of horizontal is called, to where you're looking down now, is called the angle of depression. So you hear these words, angle of elevation, angle of depression. Remember, they're always in comparison to a horizontal line. Angle of elevation goes up, angle of depression goes down, and it's compared to the horizontal. So again, if you're looking up, this is elevation, but if you are looking down, this is depression. Angle of depression. Angle of. Angle of. And notice these are parallel, so that means these are opposite interior, which means the angle of elevation down here will match the angle of depression up there. Pretty cool. And we out.